Ignition sequence start. All engines running. This is the Saturn V ascending. This is the most powerful and potent rocket ever made by humanity in full operation. This title is due to its 5 monstrous engines located at its base. Each of these engines weighed 9 tons, consumed 1,800 kilos of liquid oxygen, and 800 kilos of fuel every second, operating at temperatures around 3,200 degrees Celsius, and producing a huge amount of smoke that reached several kilometers away. Each of these engines produced 6,770 kN of thrust. A single one of these engines generated a force equivalent to the force exerted by a 690-ton block here on Earth. Besides the enormous vibrations and the deafening noise that a single one of these engines produced during operation, these engines also moved during flight. To keep the enormous Saturn V on its correct trajectory to orbit. All this power concentrated in one engine was needed because the technology in the rocket's design at the time required it. It didn't allow the Saturn V to have several smaller engines doing the same job. And incredibly, these engines were only used once and operated for 150 seconds. This is how long it took for the first stage to use up all its fuel. When it was done, the first stage with 5 engines separated from the rocket and fell toward the Atlantic Ocean. And that's where those engines remain to this day. But in today's modern world, where rockets return to Earth in a precise, controlled, and fully autonomous way, where electric cars rely much more on programming and software to be safer and even capable of driving themselves, the problems and limitations of the past have truly been left behind. Nowadays, there is no theoretical limit to the number of engines that can be placed on a rocket. In fact, it's actually cheaper to have several smaller engines on the same rocket than to have one or a few with much higher power. Besides that, the production time, maintenance, inspection, and testing of each engine, it becomes much more streamlined when there are many but less complex than when there is only one but highly complex. And SpaceX has made good use of this principle. For example, the Falcon 9 has 9 Merlin 1D engines in the first stage. Each one is capable of generating a thrust force of 854 kN. Since there are 9, that totals 7,686 kN of thrust. The Falcon Heavy, which is the higher capacity version, has 27 engines. They basically joined 3 Falcon 9s together and created a new rocket with greater capacity. But the Super Heavy has 29 Raptor engines on the same stage. But the higher the number of engines, other problems start to appear. And in particular, you have to carefully follow a procedure called the engine ignition sequence. Let's start with the space shuttles. With 15 seconds to go, a lot of water started being released onto the launch pad to absorb the vibrations and prevent them from causing damage to the vehicle itself. With 10 seconds to go, 4 spark igniters placed on the platform started releasing thousands of sparks to ignite the fuel. With 6 seconds to go, the 3 main engines were started. And here's where it gets interesting. The engines weren't ignited at exactly the same time. They were started one at a time, separated by an interval of 120 milliseconds between each one. The reason was to avoid excessive vibrations, prevent imbalances, and a few other factors. To further reduce the risks, the engines were not started at full power. Quite the opposite of the solid rocket boosters, which had to be ignited precisely at the same time, in several calculations. They were dedicated to ensuring the simultaneous ignition of both booster rockets. Any delay between the ignition of one and the other, and the space shuttle would run a serious risk of losing balance and causing a major accident right there on the launch pad. With the Falcon 9, something similar happens. But since it has more engines, 9 in total, of which 8 are arranged in a circle, they're ignited in pairs. So first, these two are started, followed by these. And finally, these ones, separated by an interval of 120 milliseconds between each. So it takes half a second to start the 9 engines of the Falcon 9. Even though during launches it seems they all start together. The reason for this ignition sequence is pretty much the same: to avoid imbalances, to avoid vibrations, to keep the loads on the vehicle within limits, and a few other factors. If you're unsure about why respecting this matters, it happened in 1959 with the Titan I rocket. Right after ignition, the rocket started to vibrate a lot, with pieces flying everywhere, and the flight termination system was activated, leading to a huge explosion still on the launch pad. In the case of the Super Heavy, you can probably imagine that firing up 29 engines at the same time, all reaching maximum power at once, must cause at least a rocket. That's why the force from the engines must be distributed through the rocket very carefully. There is a part called thrust puck. It is responsible for transmitting the force exerted by the engines to the walls of the booster as properly as possible. Keep in mind the engines don't start at full power. Since there are 29 engines forming 3 rings, the same ignition sequence used in the Falcon 9 would take 2,000 milliseconds or 2 seconds for all the engines to be started. Although it's still not very well known which ignition sequence is used on the Super Heavy. However, very long ignition times can also cause huge vibrations, oscillations, and imbalances. And the worst part is that those few extra seconds mean tons of fuel are spent while the rocket is still stuck on the pad, which compromises the rocket's maximum range. Besides that, in case of failure of one or multiple engines, some designs also use a shutdown sequence in case of engine failure. Maybe you've heard of the N-1, the largest rocket in history, developed by the Soviets. It had 30 engines that couldn't be properly tested. They used pyrotechnic valves instead of hydraulic ones. Those pyrotechnic valves could only be used once and only. It didn't do very well on any of its attempted flights, always ending in a big ball of fire. Due to the particularity of the valves in the engines, the not-so-sophisticated flight computer of the time, and the fact that the engines didn't have a gimbal mechanism, the N-1 used a sequence for shutting down the engines in case of failure of one or multiple engines. If this engine failed and shut down, its opposite would also be shut down, and so on, to keep the rocket balanced during flight. But since computers are much more sophisticated and advanced, nowadays it's no longer necessary in case of a failure of one engine for the engine opposite it to also be shut down, with computers using the gimbal mechanism and adjusting the power of the other engines to keep the rocket balanced. In fact, computers detect problems. They prevent and fix hundreds of problems that arise or threaten any rocket flight. They correct them, ensuring mission success.